So hello there. My name's Dave Hoelzer. I'm one of the co-hosts here, and I'm going to be talking to you a little bit about threat hunting and using AI with relation to it. I'm the chief of operations for a managed security provider. We do all kinds of monitoring, advanced threat hunting kinds of things for our customers. And one of the things I've been doing internally is championing AI and machine learning for about the last 10 years. And there's some amazing things that you can do in the space. And I'm not going to try to tell you everything you can do, but I wanted to share with you just one thing that we've been doing lately, and it's connected to this whole notion of threat hunting. Now, you may recognize the quote I've got there on the screen. And to me, that quote, even though it's, kind of getting dated at this point, is really at the heart of kind of threat hunting today. So I keep talking to enterprises. I've got customers that I meet with, and they tell me about their threat hunting team. And they explain to me that what they're doing is they're looking at the threat intelligence list and using those to build indicators so that they can find bad things that are happening. And they're building detection scripts in PowerShell to see what their Windows hosts are doing. But most everything they're doing is based on known stuff. If you see this happening, this is the tactic, technique, procedure that they're using. This is the signature to find. And I'm having such a hard time getting them to understand that while that is really important stuff to do, that's really not threat hunting. That's what your security operations team should be doing, is finding all of the known threats. But the idea behind threat hunting is finding the threats that you don't know what they are. And that requires threat modeling, which has been one of the primary things businesses have been asking SANS about. Can you teach our people how to do threat modeling? And the idea of threat modeling, it's sort of like an abuse case if you're doing development, right? How are we supposed to use it? But what would it look like if something bad were happening? I'm not asking, are there vulnerabilities? I'm asking, what would bad behavior look like? So in a similar way, when we're thinking about our environment, sure, I'm going to look for tactics, techniques, and procedures, but I'm also going to ask, what would wrong look like? Now, it turns out that AI and machine learning can be very, very good at this. We can go too far with it. We can do it the wrong way, and we really end up back at signature analysis. But for us, we've been thinking about how we can model some of this stuff using AI in order to do really effective threat detection. And I want to talk to you a little bit about that with regard to malware. Now, I'm certain that you've got endpoint protection tools in your enterprise. You're running antivirus at your gateway, you've got it on your mail server, you've got it at your endpoints, and that's all important stuff to do. That's security operations stuff. That has to happen. But malware still gets through. Whether it's phishing attempts to get mailed in and there's a binary attachment or it's in a PDF or something like that, whether it's the employee clicking the link, being convinced to click the link, it's a pop-up ad, whatever it is, and they're now downloading the malware. However that's happening. But the malware that we're downloading now, this is unknown malware. It has no known signature. There are things that we can do in an enterprise to really defend well against those unknown binaries, those unknown pieces of malware, but they're difficult. One of the strongest things we can do is creating an allow list. Now, there's software to help with this. It's actually something you can do natively within the Microsoft domain, but it's challenging to maintain, where we're creating effectively hashes of known good binaries, things that are allowed to run. And if you're not in the allow list, you simply cannot run. Now, if I'm someone working in a customer service center and I'm just using the web browser to answer customer service tickets, that's great. I can just run those and those systems will be really protected well. But in many businesses, people need additional applications and maybe even need to run things that not everyone else has to have. And the larger your enterprise gets, the more challenging it can be to have an allow list of only good things. There's also a false sense of security that can come in because there are a number of different things that we can put in our allow lists that can actually load and spawn additional code. So once that thing has been allowed, all of the scanning and everything else is done. But could bad things still happen? Could we use that to launch additional code? Absolutely. So is there another approach that we can use? The way we generally approach malware detection today, it really is exactly what we were doing back in 1990 or 1989 when the first antivirus software came out, looking for things like the Jerusalem B virus and the brain virus, which is really old news, but it was all signature detection. We have tried heuristic detection, behavioral based things, but even those are quite limited in our endpoint solutions because they're looking for malware like activity in a short period of time. They don't tend to monitor long term because of the resources involved. So if the new code doesn't do anything bad in a short amount of time, it assumes that it must be okay as long as it didn't match a signature. Can we do better? Can we find additional threats? Well, in your environment, do you have a next generation firewall? I'm not saying that's required, but I'm asking about it because it has a capability built into it that you may or may not be using that can be quite useful for what I'm about to tell you about. Our next generation firewalls, yes, sure, they have antivirus scanning built into them, but your next generation firewalls will typically additionally have TLS proxying capabilities built in. The ability to make it so that we can break open TLS encrypted communications going across our border and filter based on that decrypted content. Similarly, if we have strong network monitoring solutions, there's a whole bunch of different packet brokers and TLS proxies that we can put in place that really act as a machine in the middle, but it's an authorized machine that allows us to decrypt the traffic as it goes by. Now, this isn't about network monitoring. My buddy Andy, he's going to talk about network monitoring stuff. But if we have those things, we have the capability to grab copies of binaries that are passing over our network. And that's the thing I'm looking for. That's the thing that we're leveraging within our customers. There's two main ways the technique we're going to talk about is used. One is at the mail gateway, binaries that are coming in are being fed through and passed to an API with an AI solution that's deciding, is that malware or not? And I'm going to show that to you. In fact, I'm going to build that with you in just a minute. Similarly, as binaries are coming in through that next-gen firewall, copies of those binaries are being shipped off to be analyzed by this AI. In order to build that AI, so let me switch over here. I've got a Jupyter notebook up here, and this is the code that we based the solution we're using on. The solution we're using is making use of a TensorFlow model. Now, TensorFlow, PyTorch, doesn't matter. You could build the same model in either one. And what we're choosing to do is to treat the binaries as though they're images. Now that on its own is could be like a mind-blowing idea. I was talking to a Microsoft AI solution provider about this. He was in a presentation I was giving, and it just blew his mind that we were going to treat an executable as an image. And the reason I'm saying treat one as an image is that the kind of network we're going to use is typically only used to analyze images. It doesn't mean that that's the only thing you can analyze. It's really just a tool for finding features that are near each other in space. Where space here just means, like within an image. But in terms of a binary, I'm looking for shapes in the code. I'm looking for patterns in the code. Which patterns am I looking for? No particular ones. That's actually one of the beauties of machine learning. When using machine learning, I can absolutely do really detailed feature engineering. I can tell it exactly what to look at. But that requires a lot of subject matter expertise. I have to know exactly what's important. And if I'm not really an expert, that can lead to trouble. For example, I when I hire people for technical roles, will do job interviews, and I will tell people, I'm going to ask you some questions. I promise you that if I ask you the question, I know the answer. So I want you to tell me, how would you rate your knowledge in this particular area from 1 to 10, 10 being the best. People will never pick 10 because that feels really risky, but it's common to have them pick 9. And then I'll ask them a question. It is perfectly fine to say, I'm not really sure, I'd have to look that up. Because for me, if you're going to work for me, I don't have to have you know every answer, but I have to know you know when you don't know, and you know how to find out. In any event, if if you're going to say 9, you should know absolutely everything. But is it possible that you think you're a 9 or think you're a 10, but you're really a 7 or an 8 or a 6? Because you just don't know everything about it. Well, if I don't know everything about it, doing really detailed feature engineering is risky because now I could choose to include or choose to exclude a feature that actually has a really important relationship to the rest of the data that I'm simply unaware of. What does that have to do with machine learning? Well, if I exclude that feature, the algorithm has no possibility of finding that feature. So sometimes it works into our advantage to not have a deep subject matter expertise, or at least to be able to admit, I don't know. I don't know what every piece of bad code will look like. So instead, I'm going to ask the machine learning algorithm to learn on its own. The kind of learning we're going to do here is some supervised learning. And I've got some code here that's going out and trying to load in some malware. In fact, the malware repository I'm using, it's not a public one, but I have about 250,000 Windows pieces of Windows malware sitting in a malware zoo. And I'm going to use about 10,000 of them to train the model and use an approach called supervised learning. Supervised learning is a very easy idea. I'm going to tell the machine learning algorithm, here's the input data, and I'm going to tell it, and this is a piece of malware. This isn't a piece of malware. Supervised, I'm giving it the input and the answer, and asking it to work out, how do you tell the difference between those two? And find the difference without a signature, because each malware sample is different. Each non-malware sample is different. So it's not a simple signature. It's instead looking for patterns. It's looking for shapes in the code. Now I'm not going to run that piece of code live because that takes a little while to run, but I am going to load in the malware samples. And it does load quickly here. I've got a pretty beefy machine sitting behind this. And that's going to give me data that I can use to train this model. What I'm doing is pulling in all 250,000 malware samples, but I'm only going to use about 10,000 samples to train it because I only have about 10,000 non-malware executables, sort of a subset of common known good binaries off of Windows 10, Windows 11 systems. And all told, I'm going to be training this network using 20,000 samples, 10,000 of each, with 16,000 features. 16,000 bytes, 16K of data. So it's just looking at the first 16K of every binary. Why only 16K? Well, there's great advantages to that. I mean, if I use the entire binary, some binaries are quite large, and that's going to be a lot more processing for large binaries. On the other hand, malware does tend to be small. So I'd prefer to go on the smaller side. Otherwise, I could end up introducing bias. Now, bias in AI, we might think of things like racial and gender and religious bias. That can be what emerges, especially with image generation, things like that. But bias here, it is anything that can influence how the model performs. And the bias in this case would be if malware tends to be small, and many executables, known good executables, tend to be really big, well, the model could just start saying, these are small, therefore they are malware. So I want to be mindful of that bias. So rather than using everything, I'm going to limit it to 16K. That seems pretty good because malware will generally be at least that large. And now we're measuring things of the same size. The size won't be the bias. I'm also going to build some labels here. I'm going to say that ones will be malware and zeros will be non-malware. And let me just start by looking at them. I said to you, I'm going to think of them as images. So here they are. Here are some of my pieces of malware. Now, clearly, they are not images. And that brings me back to that AI solutions engineer. Because when I introduced this idea, we're going to use a convolutional network, a tool for images, for malware, just blew his mind. How can you do that? That's for images. This tool, convolutional networks, are for finding features close to each other within space. Whether it's an image, it's text, or anything else, it really doesn't matter. It's just really a mathematics tool that we can use to look at data and find features. That's all it does. Here I'm looking at these as images. I'm doing this more to make sure that it looks like the data has loaded. For instance, if every one of these pictures looked the same, I would know that I made a mistake, or that maybe my approach won't work because the beginning of every binary looks the same. But I feel like this is going to possibly do something because every one of them is different. I'm not looking for a particular thing here. I'm just making sure they kind of look different. So let me turn that into a training data set, and then I've got a model here. So my model, this is going to do some convolutional stuff, and we do not have the time. Clearly, we do not have the time to go through all of these pieces. I actually teach a class on how to build these solutions yourself. And the kind of thing we're doing here, by the way, we've got a lot of security tools out there. In the security space today, if you are a security tool vendor and you have not put AI on your label, you are not selling your product today. So everybody's got AI and is claiming machine learning. But what we can do in those tools is frequently very, very limited. So I teach people how to build any kind of AI you'd like to. And from that, you also understand better the kinds of things that vendor solutions can do, but you're not limited by what those tools can do. So in this case here, I'm using a pair of, not a pair, I've got 4 convolutional layers. I don't even remember what's in this. I built this months ago, that are trying to find these features that are then getting pushed out into a single layer to do some classification. I'm going to get that started training. Now, this will take a couple of minutes to train, but don't worry, I do have something else to share with you while this is going. Let me just make sure that gets started. Let's see if we start to see some training happening. There it goes. Okay, so I'm going to let that go. And let me just pull over here. I've got a little animation here just to explain what it is that convolutional layers do. So over on the left-hand side there, that grid, that matrix of data, you could think of that as being the bytes that make up an image, or for us, the bytes that make up a piece of malware that we've rearranged into a grid. Over on the far right-hand side, moving in and out, I've got these 3 filters, and we call them filters or kernels. They're being used to pass across. This is the receptive field. It's like a little lens. We're kind of holding our hand up and we're just looking right within that square box. We're only looking, for instance, right now at the box that has 657 across the top, 645 down the left-hand side. That's what's under consideration. And each one of those filters is being used to perform some math, and the result of that math ends up across the top. Those things across the top in machine learning lingo would be called the feature maps. The feature maps are the things that it's finding. Now, again, we don't have a huge amount of time today, but what's being found? It's actually possible, we're not going to do it now, but within the class, we take some time in the 5th day in the morning to figure out how to reach inside, pull a network apart, and then see what exactly it's doing. What are those filters finding? While the machine learning network is training, what's being updated, what it's learning, are the values that sit inside of those kernels or inside of those filters, the things that are being used to do the math to produce the feature maps up top. Now, think of it in terms of malware. That could be kind of challenging to imagine what's happening. So let me talk about it as though it were an image. Sort of the hello world task for doing this kind of work would be identifying handwritten digits. Can I tell you what the number is? If we train a network to find those numbers, there are some things that will always emerge. One of the filters, or at least one, will always learn how to find vertical lines. Another one will find horizontal lines. Another finds diagonals this way, diagonals that way, curves. And from the composite of those feature maps, it can then decide what the number is. So the intuition here is that it's looking for common shapes in code. There are things that malware tends to do, things they have in common. And it may not be in the same place, it may not be exactly the same code, but there will be shapes. And if you're an exploit engineer, a vulnerability researcher, you can think of it like gadgets, like ROP gadgets. There's going to be gadgets that appear within the code. And so the intuition is it's finding those gadgets. So once we train the network, and mine has actually already done training, let me just ask it how well it did. Now this is running live, so I mean, I'm expecting a good result here. We've only ever had a good result out of this, and I do get a really good result. Using some holdout data that my network has never seen, that is, we're using, I think it's 2,000 known good and 2,000 known malware that it was not trained on. It has an accuracy of 97%. And if I turn that into a tool that we use in machine learning to evaluate a model called a confusion matrix, it's showing me that it is, for things that are not malware, it's having a false positive rate of 4%, calling those things malware. But if it is malware, 99% of the time it's correct. Only 1% of the time it's wrong. And I've got an additional set of grids here. These are other tools and how exactly they work and what they do. That's something I teach in the class here. But sort of an important thing about it is happening up over here. There are some metrics that we use to look at a model to figure out how good it is. And people usually begin by looking at things like accuracy. How right was it? And that's a rudimentary kind of measure. It's important, but it's not the most important. Frequently, we're much more interested in how precisely we're able to identify things and how specifically we're able to identify them. So this precision and recall value, kind of technical terms to describe these values, and a measure of their composite, the F1 score. I hesitate to tell you this, but I will just give you the name. The F1 score is the harmonic mean of those two. So that's not the mean. That's not add them together and divide by 2. It's a little more complicated than that. But usually, precision and recall, usually they are opposite measures. And usually there's a tension in our models that if our precision is good, our recall will be worse. And if our recall is good, our precision will be worse. And we're trying to balance the tension between them. But in rare cases, we can get both values to be high. So what we've managed to do is maximize not the accuracy here, but the F1 score, the tension between the two. And that's what these graphs at the bottom are showing. In these graphs, this orange line is showing what an absolute guess would be if we just randomly guessed. Yet we are way up in the left-hand quadrant. The further up in the left-hand quadrant you are, the better the model is. What is this saying? This is saying that the model that we just built is something like 96, 97% accurate in identifying unknown malware. Now, every time you train this model, it will be slightly different. And it has to do with how models get trained. They're actually randomly initialized. The one that we're running in production is trained in exactly the same way. And that model is 99% accurate across both classes. The way that we end up architecting this, let me try to get the right thing on the screen. The way that we end up architecting this is that from that next generation firewall, so this could be firewall sitting out there, and sorry, my pen is awfully large here. Let me make that a little bit smaller. And maybe from our email gateway, email is sitting over here. What we're doing is running this model in an API. It's just running in a Streamlit API, and it's sending queries out to that, forwarding in the first 16K of the malware, and this can now return back if it's good or if it's bad. So this is all the way from concept through deployment, how this stuff can be used live, how we can use it in the real world to do threat hunting. Because the malware we're finding here, make sure you get this. I'm not finding known malware with this. I don't need this tool for that. And this tool is not to replace your endpoint protection, by no means. What this tool is able to do is identify malware for which there is no known signature because it's unknown. How useful would it be for you if when one of your employees goes out to the internet and he downloads some software, if your environment were able to tell you that might have been malware? 99% accuracy. Not every one of them will be right, and you will still miss some. But how are you detecting unknown malware today? Or if you're working an incident, you have a compromised machine, and your intuition tells you malware is involved, and you've tried every endpoint scanning tool you have, and it's not known malware. You may have the ability to do reverse engineering of malware, but to do the reverse engineering, you have to know which file the malware could be in. So what if you could go from 15,000 executable files on the machine down to a handful, maybe 4 or 5 that might be malware, so that you can now apply your reverse engineering techniques? That's the kind of thing that this allows us to do. And we are running this live within environments today. The way we're running it, I mentioned to you with the next gen firewall, things like that. We're actually using Zeek or Corelight, which is something that we teach extensively in the 503 class. Kind of, I mean, there's a huge amount of stuff in that class, but a major thing you get to learn is how to detect things without signatures, in addition to all the signature detection and all that kind of stuff. In fact, Andy Lehman's going to be on our program today. He's become sort of the primary instructor for that class, and I'm kind of excited to hear what he's going to talk about. On the other hand, if you're interested in like doing the stuff I'm talking about yourself, building those models, this model here is actually one of the ones that we build in the class. Every single thing we do in the class is applied machine learning, not just theory. We give you the theory so that you can build an intuitive sense of how to approach the problem and learn how to turn the data you have into things you can actually do machine learning with. Think of it as, we talk about actionable security. Think about it as actionable AI. How can I take what I have and make it something I can use for doing AI and influencing in improving my business process for us, for our security process? So that's the SEC 595 class. If you have other questions, you're welcome to reach out to me. There is a QR code up there for me. You can connect to me on LinkedIn and send me questions. Otherwise, I think that's going to be it for me for right now. Thanks for your attention. Let's hand it back to John.
Thank you so much, Dave. Super cool stuff. Every time we talk, my mind is just blown with all sorts of like amazing things that you're doing there. I don't know if anyone here in the presentation has seen 595, but one of the things that stuck out to me with that class when I was able to sit in on it for a few days is I was like, the underpinning to explain a lot of this stuff seems very complex, but Dave does an outstanding job explaining math better than literally any professor I've ever had going through an engineering degree, which is a lot of math professors. Your heavy reliance on explaining the intuitional kind of way of understanding things, I think, really makes things clear that would otherwise be very complex and kind of, I don't know, obtuse kind of stuff to understand. So always love when you do these presentations. You had the amazing animation. How did you make that animation? What software does that?
I'm using a tool called Manim. It's actually created
Okay.
by a guy. He does a whole bunch of YouTube stuff, but it's
Yeah.
it's just it's a math animation library. It's phenomenal.
Is it the one from Three Blue, One Brown
You
or
got it. Three blue,
Yep.
one brown, something like
Yep.
that. Three brown,
Yeah,
one
yeah.
blue, whatever his name
Or
is.
yeah, I always forget the numbers, but yes, outstanding math channel if anyone's here
It's
for the
very, very
math
good.
and want to dive deeper on that. Yeah, I recognize the style. That's great stuff. So always good to kind of see those details in there. So thank you so
Well,
much
thank you
for
very much,
the
Sean.
presentation. Great stuff.
Thank you.